Hi everyone, in this video we are going to discuss carbon dating, which is more formally referred to as radiocarbon dating technique, okay? It really just depends on who you're talking to and how they learned about carbon dating originally. Sometimes you'll even hear people refer to it as C14 dating, which is fine. We all mean the same thing. We're basically just saying that we're going to use the half-life of the radioactive sample carbon-14, and we're going to use this information to back calculate and actually determine how old a sample is. And so we use this a lot of times for fossil fuels, or if we find some dinosaur fossil something, we basically just try to use this information of carbon-14 to back calculate and see how old the sample was. And so the first thing we need to understand in order to do this properly is that a living organism has a very, very unique and set ratio of carbon-12 to carbon-14. So let's get this down here. A living organism, so something that is alive, always has a ratio of carbon-12 to carbon-14. It's very specific. There's always one carbon-14 to every 1 times 10 to the 12th atoms of carbon-12. So now, while your organism is alive, this is going to be its ratio. And just think about it. Every time you breathe, you're exchanging carbon dioxide into and out of your system. So you're always exchanging carbon-12 and carbon-14 with the atmosphere. But once you die, you're no longer breathing, and so you no longer maintain this ratio. So no longer maintain this ratio. Okay, so what we can see is we basically determine how much, when we find a sample, we determine how much carbon-14 there is, and then we can say, okay, we know that it takes 5,715 years in order to decrease that concentration by half. And so we just use that information to go backwards. Okay, so then usually we are within 10% of the true value. Okay, which is fairly accurate if you actually think about what we're calculating here. We're trying to go back millions and millions and millions of years and try to figure out exactly how old something is. And so for us to be within 10% of the true value, that's actually pretty good. It's decent, it's not great. Okay, we could definitely be better. So let's do a calculation together here. So how old is a fossil that has a ratio of carbon-12 to carbon-14 of 1.25 times 10 to the 11th atoms of carbon-12 to every 1 carbon-14 atom. Okay, go. All right, did you get an answer? Hopefully you did, but it was a little bit tricky. It was definitely challenging, and you had to be methodical about how you worked through this. So there's several different ways that you can do this. This is just my own personal approach. So the first thing I do is I set up two different ratios. I have an alive ratio and a dead ratio. And so what I like to do is put my carbon-12 over my carbon-14 and set these equal to each other. Okay? So there's my basic formula. And then what I'm going to do is just plug in some numbers. So when something is alive, we know that it has 1 times 10 to the 12th carbon-12 atoms for every 1 carbon-14 atom. But now we know for our dead sample of this specific fossil, we have 1.25 times 10 to the 11th atoms of carbon-12, and we're trying to determine specifically what that means or what that tells us about our carbon-14. So if you solve this out, what you will see is that your carbon-14 has decreased by an eighth. Okay, which is kind of a weird number. If people kind of get lost and they get confused, what does that mean? So that doesn't tell you about the half-life. That tells you how much of the concentration of your sample still remains. So then what you do is you come up with a little chart. And so you say, okay, I know if I start with 100%, and I go to 50%, that is half of my sample that is decreased. After 50%, I go to 25%. That's another half, which is actually a quarter, right? A quarter of our sample remains. Now, if we do another iteration, we get down to 12.5, and that is actually an eighth of the original sample. So this is 1, 2, and 3 half-lives that have occurred. So what we do is we take the half-life of carbon-14, which is 5,715 years. We multiply that times 3 because 3 half-lives have occurred. If you do this properly, you will see that you come up with a number of 17,145 years, which means the fossil that you found is 17,145 years old. Cool, right?